So last time, if you remember, what we did was we started looking at percentages. And basically with percentages, you know, we saw what they were. We saw that, what do you call it, that fraction is over of, part over whole. We also saw absolute change, and we also saw relative change. And then we came across a new function, actually. A new function called an exponential function. It was very different than a linear function, mostly because a linear function, you change the output by, the output changes by adding or subtracting a fixed number. You know, that's what the slope was. For exponential functions, they change at a constant percent. In other words, to get the new output from the old one, you know, if you increase x by 1, you take a percent, you add on a percentage of the old output to get the new one. In other words, the relative change of your output, that's always going to be constant at r with exponential functions. Whereas with linear functions, the rate of change, the difference in output values alone, that's always constant. The absolute change is constant. And again, this is what exponential functions look like. This is really what I'm trying to say. If you increase x by 1 unit, the relative change here for an exponential function is always going to be r. That's always going to be r. Okay, with a linear function, we would just have the numerator, and in fact, the numerator would just be the slope. But here, though, we have this. And our exponential functions, remember, look like this. We have a times 1 plus r raised to the x, where r is the relative change, or if you want the percent change as a decimal. You can also have this 1 minus r. In this case, the exponential function, it's decreasing in value, whereas in the up here, it's increasing in value. So that's what's happening here. Okay? And again, here, the negative indicates that it's decreasing in value. So that's what exponential means. Now, if I were to give you r and a, you can calculate an exponential function. You know, you can easily do that. In other words, if you know what r is and a, you can come up with an exponential function easily. And to go the other way around, you can. That is, if you have something like this, you can calculate, a you can calculate easily, either by looking at it or replacing x by 0. And you can also get r back from b. Namely, if b is positive and less than 1, then r has to satisfy this, and so does b. And you can get r from here. If b, however, is greater than 1, then we get this instead. And it turns out those are the only cases. With exponential functions, the base b here has to be positive, and it can't be 1. So these are the only possibilities. So to illustrate that, here, let's suppose we have this exponential function, and we want to figure out r. So since, okay, the base b here, 0.85, is less than 1, we have to have this. We have to. And what we can do is we can obtain r from there easily. It's just basic algebra. It's almost like r is taking the role of x here, so to say. Although I don't want to say that because x is up here. But I think you get the idea, as you can see. Basically, we can solve for r easily. I mean, I'm going through the calculations. Again, I don't know everyone's math background here. So I'm erring on the side of caution. Okay, so that's what I'm doing. And we get R is 0.15. All right. So that's what we get here. Now, okay, so we get R is 0.15. And again, if B were greater than 1, like in this case, we can still get R. Also, again, I did email everyone the notes. Just letting you know, I will post the full notes later on and the videos as well. So this is what we have here. But we can get R from this, right? Because we know since B is greater than 1, R has to satisfy this. So let's get R. We subtract. As you can see, we just subtract 1. We get R is 0.3. So we can get R from the exponential function. Okay, that's good. The book does go through that as well. That's why I'm doing this. And this is what I was saying before, that if you want an exponential function that has a specified growth or decay rate and initial value, you can come up with an exponential function like that easily. For instance, if you have 16% as your growth rate and the initial value is 100, this would be our exponential function. Remember, the percent you convert to a decimal. Okay, the initial value here, right? That's 100. And the growth rate, because since it's growth, right? They said growth. So since we want growth rate, we do addition. Because again, the function is going to grow in value. It's going to increase. For decay, so the only difference here is that we want the function to decrease. That's what decay tells us. If it decays, it's breaking down, getting smaller. In that case, we do this. 1 minus. With subtraction, that function is going to decrease in value. Okay, that's good. And now the book does something like this as well, and I thought it was really good to do. Basically, here we can fill in the entries in this table. Namely, each row corresponds to a certain function. So for instance, in the first row, right, we have this function. So the initial value would be 615, as you can see, right? The growth or decay rate, right? Growth would be, as you can see here, it's growth because, we have growth here, right? Because the base, the 1.25, is bigger than 1. Okay? Not only that, we can easily get R, the growth rate. Because we have this, that tells, since this is greater than 1, we must have 1 plus R equal to the base. We must have 1 plus R equal to the base. Okay? And so how do we get R? We subtract, like so, as you can see. And we get R is 0.25. For this, just like the top row, and just like before, our initial value is 300, okay? As you can see from here. I mean, you could replace X by 0, but it should be easy to see the initial value is here. That's the number in front. Here, we have growth or decay, right? Well, in this case, we're going to have growth. And why is that? Because the base here, 1.09, is bigger than 1. And just like the one above it, we can get R as so. We subtract, basically. And we get 0.09. Okay, for the next one, what's the initial value? Well, that's 3,900, right? You can see that from the front. Here, 0.95, well, that's less than 1. So we're not going to have growth here. We're going to have decay. And how do we get our R? Now, how do you get R then? Well, 0.95 is 1 minus r. So it's really just like on the first slide. We just get r by subtracting. I mean, I didn't show the calculation here. It's similar to what's on the first slide. So we'll just go by that. Good. Okay. Now here, we don't know the function, but we have enough parameters. Namely, we have the initial value. We also have the decay rate. Oh, excuse me, we have that as decaying and the rate as a decimal. I mean, you could have the rate as a percent, but then you have to convert to a decimal. So how do you get this function? Well, it's got to look like this. That's the initial value. We have our rate, and it's decaying, so we have to have minus. Below, I mean, the initial value is 1,200. We have the same rate, though. Growth is addition, as you can see. Growth is addition. Okay? Good. Okay, let me just pause the recording. Let me just stop the recording.